Hey everyone, hopefully at this point you've watched the intermolecular forces video number 1 and number 2. I have a little recap and activity for us. So if anything, we need to know the difference between intramolecular forces, which is talking about bonds, so the actual forces that are holding atoms together in a molecule, versus intermolecular forces, which we usually abbreviate IMF, just so you're aware. Intermolecular forces, that's the attraction between molecules. So you'll hear me talk a lot about clones. If I take a molecule and I clone it, how are those clones attracted to each other? So I'm going to focus on the intermolecular forces that's between clones, and I'm only going to really focus on ones that occur in covalent molecules, so talking about polar, nonpolar clones interacting with each other. Really, when we talk about ionic things, that's more lattice energy, right? We learned about the ion-ion forces in lattice energy in our first objective, okay? So let's talk about nonpolar clones. If I clone nonpolar molecules, noble gases or single elements, they are going to experience London dispersion forces. The attraction happens due to temporary dipoles. So for a hot second, the electrons move to one side, creating a temporary partial negative and partial positive, so temporary that we don't even write it down. So we're not going to write this down on our paper like we do for dipole. It's just for a hot second, electrons are to one side, and that causes the other molecules to do the same thing right next to it. It's a quick attraction. Almost imagine if you had the ability to turn the magnetic power on and off of something. That's what's happening. It flicks on and off, and it happens often enough that those guys are attracted. If we have large complex molecules, that means they have more electrons, which means the electron cloud is more polarizable. That is a big buzzword, polarizable. It just basically means that the temporary dipoles occur more often when it's more polarizable, which results in stronger London dispersion forces. Similar idea here, but if I clone polar covalent molecules, so I'm talking about a molecule that has a dipole moment, right? A partial positive and a partial negative in the molecule permanently, and I clone that molecule, that attraction is because the partial positive in one molecule is attracted to the partial negative in the other molecule. The stronger the dipole moment, so when I'm looking at one molecule, the bigger the difference in electronegativity, like essentially the stronger the polarity of that molecule is, the stronger the dipole forces is between those clones. So strong, big dipole in a molecule, you clone that molecule, very strong dipole intermolecular force. The hydrogen, and I put air quotes, bonding forces, because this still is an intermolecular force, even though it has the word bond, is just a special case of dipole. I call it dipole on steroids. So if I have a polar covalent hydrogen bonded to the fun elements, F, O, or N, because it's so much fun, we have a dipole that's occurring, but it's an extrapolar bond, right? Hydrogen bonded to F or N is going to be a big difference in electronegativity. It is extrapolar. Hi, Phoebe. And then what happens is I get an extrapolar molecule. When I clone that extrapolar molecule, the extra partial negative in one molecule is attracted to the extra partial positive in another. So if I were to draw this on paper, it would look just like dipole, but the difference is this is an extra strong dipole force. I call it dipole on steroids. It's called hydrogen bonding forces. So I think it's helpful to have a strategy when solving these problems. First thing, AP wants you to always talk about both molecules or atoms. So if they mention two things or three things, you have to talk about all of them in your answer. That's gross, Phoebes, she's just coughing. One thing that you need to know is always double check that you answered the question. If they ask for boiling point or states of matter, anything like that, make sure you always circle back and say, because it has the strongest intermolecular force, it has the highest boiling point, or it is a solid at room temperature. So here's kind of the order that I do things in solving these problems. For each molecule, I identify the types of bonds present. So if they give me two things to compare, I say the types of bonds. Then I will identify the intermolecular forces present in each molecule. If there's only London dispersion forces in both molecules, I look at the size. Which one has more electrons present? Because the one with more electrons is more polarizable, so there's more London dispersion. Or I look at complexity. Is it a long chain or is it bulky? If something is a long chain, that is going to have a stronger London dispersion force than something that's bulky and hard to interact with, right? If I clone something that maybe has a shape like this, that's harder for another molecule to come in and interact with, right? Versus if I have a long chain molecule, that's easier for another long chain. Look at all of those places they can interact there versus just right here, okay? If it's dipole-dipole, so they both have dipole-dipole, then I'm going to look at the difference in electronegativities for those polar bonds. And I also will look and see if it can do, if it's a longer molecule or a large molecule, can it dipole-dipole interact in multiple locations? So maybe I have a long molecule and there's the ability to form a dipole on this side and on this side versus a molecule that can maybe only has a polar piece on that side, right? This molecule right here has two places that if I were to clone that molecule, it could do dipole-dipole, whereas this one just has one. And then if it's hydrogen bonding, you're going to look for the same type of thing, but you're looking for those F, O, or N bonds in a molecule. A lot of times AP will not just say who has the strongest intermolecular force. They want you to talk about properties, or they'll say here are the properties justified. So let's talk one, state of matter at room temperature. If something is a solid, it means it's really attracted to itself, high intermolecular force. A gas at room temperature, low intermolecular force. Boiling point is the temperature that something boils. So going from a liquid to a gas. So that means I'm breaking the attraction between the liquid particles to get them to the gas phase. So I'm breaking IMF. So if something has a high boiling point, high temperature, that means it's strong intermolecular forces. Low boiling point's the opposite. Melting is very similar. I'm going to go from solid to liquid. So I'm breaking the intermolecular force of the solid to get to the liquid, high melting point, strong IMF, low melting point, low IMF. Viscosity is the resistance to flow. So something like trying to pour it out, something with a high viscosity is very attracted to itself. It's like sticky. So high intermolecular force, and low viscosity, not that strong of intermolecular force. Vapor pressure is really the only one that feels opposite. So if we have a high vapor pressure, that means there's low intermolecular force. It means the molecules are easily going from the liquid to the gas phase at equilibrium. And then low vapor pressure is the opposite, high attraction, so it stays in the water phase more than the gas phase. So here's 3 typical practice problems: highest boiling point, lowest vapor pressure, and then another lowest vapor pressure. Let's look at this first problem. This guy. We want something with a high boiling point. That means we're looking for the strongest intermolecular force. So I go through each one and say the type of molecule. HBr is a polar bond, and there's only one thing bonded to another, so it's a polar molecule. Kr is just a noble gas, so it's nonpolar. And Cl2 is a diatomic, so chlorine to chlorine, they're going to share equally, nonpolar. So that means because we have a polar molecule here, this guy will experience London dispersion because everything has London dispersion, and dipole-dipole. This guy just has London dispersion. This guy just has London dispersion. I want the strongest intermolecular forces. That's going to be HBr. All right, next we have vapor pressure, and I want low vapor pressure, which means it's a strong intermolecular force. So here's the idea. If I have a liquid in a closed, sealed container, some of those liquid particles are going to evaporate to be a gas, and some of the gas is going to evaporate to be a liquid. But if I measure the pressure of the gas, that means more of the liquids are turning into the gas phase if the pressure is high. So if I have a low vapor pressure, that means not a lot of the particles have turned to the gas, and they're staying in the liquid phase because they're attracted to each other. So low vapor pressure in that container means strong IMF. So let's go through our steps. First, I say what type of molecule we have. Cl2 shares equally, nonpolar. Br2, nonpolar. I2, nonpolar, right? Something bonded to itself always shares equally. So London dispersion, London dispersion, London dispersion. What do? We look at complexity. So I'm going to add up how many total electrons. 2 chlorines will add together to be 34 electrons, 74, and then 106 electrons in these molecules. And so I2 has more electrons, meaning it's more polarizable, more temporary dipoles, which means stronger London dispersion, which will result in a lower vapor pressure. Notice I remembered to answer the question about vapor pressure. All right, same thing here, low vapor pressure. So we're looking for the one with the strongest intermolecular force. I have this carbon chain, so carbon with hydrogen, carbon with hydrogen, carbon with hydrogen. I have a carbon chain, and I know I drew over it, but this is a double bond to an oxygen, so I drew a dipole, and then a carbon chain with an OH at the end. So we have a nonpolar molecule. We have a polar molecule because this is the dipole in the middle. And then we have a nonpolar chain with polar on this side, right? That's a polar bond. So this guy's got London dispersion. This guy's got London dispersion and dipole, because if we clone this, we can do dipole right here. And this guy has London dispersion here between its clone, but I have that special hydrogen directly bonded to an F, O, or N. And so if I clone this side of the molecule can do London dispersion, and this side can hydrogen bond with that same section of the clone. So the strongest intermolecular force is going to be this guy because it's capable of hydrogen bonding. All right, I have an activity. We're going to do it a little modified because we're obviously at home this year in 2019, 2020. But here's the idea. So there's some background info if you need electronegativities. They are on this chart. You are going to get an assigned molecule or a couple assigned molecules. These colors correspond to the elements, so that will come in handy. And then just a reminder of how to classify if a bond is polar, nonpolar. Don't forget carbon to hydrogen is always going to be nonpolar. So these directions are a little more specific for if we're in class, but I'm actually going to go through each step for an example, but feel free to refer back to these because you're going to do these steps on your own. This year, you're not going to draw anything on this page. You're actually going to upload on Canvas. You're going to answer some questions and upload a photo of your drawings, whether it's on a whiteboard or a piece of paper. I don't really care, but you're going to upload those into a discussion on Canvas. It's called Intermolecular Forces Discussion Activity. So first step, you're assigned a molecule. So I assigned myself this guy. And if you look on that first page, the red is hydrogen and the blue is oxygen. So after you get your molecule, step number 2 on the list says to label the bonds or the intramolecular force. And so if I find the difference in electronegativity, 3.5 minus 2.1 gives me 1.4. So that makes this bond right here polar covalent and that bond polar covalent. So I'm going to label those. Step number 3 says to label the dipole. So because oxygen is more electronegative, I'm basically getting a mini dipole here, or I should say a large dipole, partial positive, partial negative, partial positive, partial negative. But if you look, both of those arrows are pointing in the same general direction. So I actually just drew one dipole arrow for the whole molecule showing the overall direction. We will only do this step where we label the dipole if it is a polar molecule, right? If it's nonpolar, there are no permanent dipoles labeled. Step number 4 says to arrange the molecules to essentially increase the attraction. So for example, I wouldn't put a blue molecule right here because I know oxygen and oxygen are not going to attract. So that's what it means when it says to maximize. So basically, I just spaced out my molecules. I also want you to do 5 molecules total. So you will draw 5 more molecules or 5 total molecules. Step number 5 is to label all of the intermolecular forces. So I have these polar molecules, so I know the partial negative. Get my pointer. I know that the partial positive of this hydrogen is going to be attracted to the partial negative, but because this hydrogen is directly bonded to an F, O, or N, instead of calling this dipole, it's actually called hydrogen bonding. It's dipole on steroids. Because this is AP, I'm also going to add a note in London dispersion forces because London dispersion is everywhere. And if you ever have a molecule that's just London dispersion, remember we don't have a permanent partial positive, partial negative. So I personally don't really care how you draw. Like if you drew blue to blue and called it London dispersion, I would be okay with that. That's fine because it is the London dispersions due to temporary dipoles, temporary movement of the electrons. Okay, so this is where you try. So you're going to look at the directions right now on the intermolecular forces activity discussion, and you have to do 4 of these. And it tells you what I want for each one. This should take you about 15 minutes. So if you find that it's taking you longer than 15 minutes, either A, ask for help, because you're getting stuck, or B, stop trying to be Pablo Picasso with these drawings. They're meant to be quick. So number one, I want everyone to try this molecule. So you're going to do those steps I went through, labeling the bonds and the dipoles if appropriate, cloning the molecule, drawing the forces. You'll do that. For this molecule, I want 5 of them drawn. Number 2, if your last name begins with A through D, this is your number 2 molecule. Same process, but with this guy. Number 2, if your last name is E through O, so this is your molecule that you will do those same steps for number 2. This is number 2 for P through Z. So if your last name is P through Z, this is the molecule that you're going to do for your number 2. Number 3, everyone, you're going to have a mixture of these guys. So you're going to mix these 2 molecules together. Let's do 3 drawings of those and 3 of these. So you'll have 6 total molecules in your drawing, but you'll label each of these and label all the possible intermolecular forces for number 3. And everyone will also do number 4. So we want 3 of those guys and 3 of this guy. So you're going to follow the directions on the discussion and post your drawings with the labels, making sure you include everything. And I'm going to try to hop on and put some comments to make sure we're really understanding this. Good work.